We're now going to apply the notion of Dirichlet convolution to a specific scenario known as summatory functions. Now we've introduced Dirichlet convolutions, studied some properties, commutativity, associativity, and some stuff regarding inverses. But from this point forward, there's one very specific convolution that we're going to be interested in. For an arithmetic function f, the summatory function of f is the convolution of f with the 1 function. Remember that this big fancy 1 just stands for a function that is always equal to 1. Typically, if f lowercase is an arithmetic function, then f uppercase is going to be a summatory function, and the summatory function of little g would be big G, etc. This is just our notation convention. It's of course not required. So if capital F is the summatory function of f, well then capital F of n is the Dirichlet convolution of f with the 1 function. But this is a Dirichlet convolution, so we look at all positive factors of n and perform this summation. But now the 1 function is simply always equal to 1, so we don't really need to bother writing it. So the summatory function on n is the sum of the original function on all of the positive factors. And this convention is not necessarily universal regarding lower and uppercase letters. We might end up letting capital F be the summatory function of f, and then if I want to take the summatory function of that, we don't have like double capitals, so we might just use capital G. If the summatory function of little f is big F, we might sometimes call little f the anti-summatory function of capital F. So capital F is the summatory function of little f is the anti-summatory function of capital F. And I should point out this is not standard terminology. As far as I'm aware, there's not a standard way to refer to one function as the function whose summatory function is the other one. So I call it the anti-summatory function. Let's take a look at an example. Suppose f of n is 3n minus 1. This is not a multiplicative function. I know it's not a multiplicative function because f of 1 is not equal to 1. But let's let capital F be the summatory function of little f. Can we compute the value of capital F of 18? Well, all we have to do is directly compute that capital F of 18 is the sum of the positive divisors of 18 of little f of those divisors. Well, the divisors of 18 are just 1, 2, 3, 6, 9, and 18, so I plug all of those into the function little f and compute. F of n is 3n minus 1, so f of 1 is 2, f of 2 is 5, f of 3 is 8, f of 6 is 17, and so forth. And now I add all these up and I get 111. So capital F of 18 is 111. Let's take a look at another example. Compute capital T of 216,090, where capital T is the summatory function of tau. Since tau is multiplicative, so is capital T. How do I know that? How do I know that the summatory function of tau is going to be multiplicative? Because the summatory function is the convolution with the 1 function. And the 1 function is multiplicative, and the convolution of two multiplicative functions is multiplicative. In other words, if a function is multiplicative, so is its summatory function. So since tau is multiplicative, so is capital T, the summatory function of it. So we're not going to attempt to compute all the positive factors of 206,090. Rather, since we know capital T is multiplicative, I only need to know how it acts on prime powers. And prime powers have pretty easy factors to list out, right? Capital T of p to the k, I list out its positive factors and plug them into tau, and the positive factors of p to the k are just 1, p, p squared, and so forth, all the way to p to the k. Now tau of 1 is 1, tau of a prime to the first power is 2. Remember that tau of p to a power is just that power plus 1. So 1 is p to the 0, so 0 plus 1 is 1. Tau of p to the first, 1 plus 1 is 2. Tau of p squared, 2 plus 1 is 3, and so forth. And if I simply add all these up, there's a pretty well-known formula to do so. It's going to be k plus 1 times k plus 2 over 2. Okay, the sum of the positive integers from 1 up to a stopping point are that number times the next one over 2. So now I can simply rely on the prime factorization, which isn't that difficult to determine, that 216,090 can be written as 2 times 3 squared times 5 times 7 to the 4th. Therefore, tau of that number, capital T of that number is T of 2, T of 3 squared, T of 5, and T of 7 to the 4th. And we have this formula now that says capital T of a prime power is the power plus 1 times the power plus 2 over 2. So this is T of 2 to the first. So the next number would be 2. The one after that is 3 over 2. T of 3 squared is going to be 3 times 4 over 2. T of 5 to the first is going to be 2 times 3 over 2, and T of 7 to the fourth is going to be 5 times 6 over 2. And if you compute all of this out, it works out to be 810 exactly. So we did not have to list out all the positive factors of 216,090. Because the summatory function of a multiplicative function is multiplicative, it was much easier to simply determine how capital T acts on a prime power, and then rely on multiplicativity to get us to the end. More examples are good. Let f of n be n plus 1 and g of n be 3n squared. Define capital F to be the summatory function of f and capital G to be the summatory function of g. Compute the convolution f star g of 10. Now, unfortunately, neither f nor g are multiplicative, so there's not much to do except attack it directly. The convolution of f and g just requires listing out the positive factors of 10. Those are 1, 2, 5, and 10, plugging one of them into capital F and one of them into capital G. So now we just compute each term individually. Looking at the sum above, we need to know capital F of 1, of 2, of 5, of 10, and similarly for capital G. Well, capital F of 1 is the sum of all the divisors of 1, plugging it into F. There's only a single divisor of 1, and little f of 1 is just 1 plus 1, which is 2. On the other hand, capital G of 10 says take all the positive factors of 10 and plug them into little g. So I have g of 1 plus g of 2 plus g of 5 plus g of 10. G of n is 3n squared, so this is 3 times 1 squared, 3 times 2 squared, 3 times 5 squared, 3 times 10 squared. It works out to be 390. In the next term, we have f of 2 and g of 5. F of 2, take the factors of 2 and plug them into little f, f of 1 plus f of 2. Since f of n is n plus 1, this is just 2 plus 3, aka 5. G of 5 is going to be take the positive factors of 5 and plug them into little g. So this is going to be g of 1 plus g of 5, which works out to 78. Remember that g of n is 3n squared. Similarly, for the next term in the sum we're interested in, I need f of 5 and g of 2. So I take the factors of 5 and I plug them into little f. F of 1 plus f of 5 is 8. For g of 2, I take the positive factors of 2 and I plug them into g. G of 1 plus g of 2 is going to be 15. For our last term, we have f of 10 and capital G of 1. Capital F of 10, take the positive factors of 10 and plug them into little f. So I have f of 1, f of 2, f of 5, f of 10. Since f of n is n plus 1, this is just 2 plus 3 plus 6 plus 11, which works out to be 22. Capital G of 1, on the other hand, says take all the positive factors of 1 and plug them into little g. So this is just little g of 1, which is just 3. Now altogether, I have 2 times 390 plus 5 times 78 plus 8 times 15 plus 22 times 3. Just going back to this original way we wrote out the Dirichlet convolution, capital F star, capital G of 10. And now we compute this whole sum and we get 1356. Okay, not the most fun problem we've ever done, but relying only on definitions, we were able to kind of hack through it. We can continue working more and more complicated examples. So here's one. Let f of n be n times mu of n, where mu is that Mobius function. Let capital F be its summatory function, but then let capital G be the summatory function of capital F. So we're taking the summatory function of the summatory function of this function here, n times mu of n. Can we compute capital G of 3400? Now, if we attempted to do this the same way we did the previous slide, to compute capital G of 3400, we would say G of 3400 is the sum over all of the positive factors of 3400, capital F of that, but each one of those terms, capital F of a divisor, would be the sum over factors of that factor, and computing little f, it's quickly going to turn into a nightmare, especially since 3400 has a good quantity of positive factors. But instead, let's do it this way. N is a multiplicative function. The Mobius function is a multiplicative function. The product of two multiplicative functions is multiplicative. Therefore, lowercase f is a multiplicative function. The summatory function of a multiplicative function is multiplicative, so capital F is multiplicative. The summatory function of a multiplicative function is multiplicative, and since capital F is multiplicative, so is its summatory function, capital G. So capital G is actually a multiplicative function, which means we only need to know how it acts on prime powers. If I can figure out what G of a prime power is, I can then rely on the fact that 3400 is 34 times 100, so the prime factorization falls out pretty quickly. But G is the summatory function of capital F. So to determine how G acts on prime powers, first let's figure out how capital F acts on prime powers. Well, capital F of a prime power, I just need to sum up over the factors of that prime power little f, because it's the summatory function of little f. F of d is just d times mu of d. That was our original definition of the function little f. And in quick succession, two nice things are going to happen. First, the positive factors of prime powers are easy to list out. It's 1, the prime squared, all the way up to p to the k. So I simply take all of those, I plug them in, and I sum up the result. The second nice thing that happens is that the Mobius mu function spits out zeros a lot. Okay, mu of 1 is 1. Mu of p is minus 1. So for the first term, I get 1 minus p. But every term after that has p to a power 2 or larger, and mu of a prime squared or prime cubed and so forth are all 0. So all of these terms are just zeros. So f of p to the k is simply 1 minus p. Notice that it doesn't matter what k is. F of p to the k is 1 minus p. It is important that k be at least as large as 1 so that this term here shows up. But if k is 2 or 3 or 4 or whatever, I just get a bunch more zeros and that does not change the value. So no matter what k is, as long as it's positive, f of p to the k is 1 minus p. So what's f of p to the 4th? 1 minus p. What's f of p to the 8th? 1 minus p, and so forth. Now I can try to compute capital G of p to the k. Capital G is the summatory function of capital F. So to compute capital G of p to the k, I take all the positive factors of p to the k and I plug it in. But again, the positive factors of p to the k are just 1p, p squared, up to p to the k. And now, capital F was known to be multiplicative. So capital F of 1 is 1. Past that, I have positive powers of primes, and I know that capital F of a positive power over prime is always 1 minus p. Capital F of p, 1 minus p. Capital F of p squared, 1 minus p, and so forth and so forth and so forth and so forth. So I have this single 1 at the very beginning, and then I get a copy of 1 minus p for each power of p in this list. From the first, the second, up to the kth. There are k of them. So ultimately, we have a 1 plus k copies of 1 minus p. So G, capital G of a prime power, is going to be 1 plus the power times 1 minus the prime. It's an odd little formula, but it works. And now, G of 3400, since capital G is multiplicative, I can split 3400 into its prime power factorization. Here I have 2 cubed. So the prime is 2 and the power is 3. So G of 2 cubed is going to be 1 plus 3 times 1 minus 2. 1 minus 2 is negative 1. So 1 plus 3 times negative 1 times G of 5 squared. So the prime is 5 and the power is 2. 1 plus 2 times 1 minus 5. 1 minus 5 is negative 4. 1 plus 2 times negative 4. And finally, G of 17, aka 17 to the first. So the prime is 17 and the power is 1. 1 plus 1 times 1 minus 17, or 1 plus negative 16. Compute all this out and you end up with negative 210. So without having to list out all of the positive factors of 3400, we determined that capital G of 3400 must equal negative 210. Moving on, more examples. Here's a theorem. Tau, the quantity of positive divisors function, is actually the summatory function of the 1 function. Now, since the 1 function is multiplicative, so is its summatory function, and we're temporarily going to call that function f. We just need to determine that f is equal to tau. But let's go ahead and compute. The summatory function of the 1 function is multiplicative, so I only need to know how it acts on a prime power. So I list out all of the positive factors of p to the k, 1p up to p to the k, and I plug them into the original function, which is always equal to 1. Now I have a 1 for every power of p starting at p to the 0 and ending at p to the k. That's k plus 1 total 1s. So whatever the summatory function of the 1 function is, f of p to the k must be k plus 1, but that's actually the same as tau of p to the k. So the summatory function of 1 is multiplicative, tau is multiplicative, and on prime powers, they are exactly the same thing. Therefore, they are always equal. So I have two multiplicative functions that agree on prime powers, so they're the same function. So the summatory function of 1 is actually just the function tau. All right, so let's talk about what we've done here. Tau, which we've already discussed, is in fact just the summatory function of the very, very straightforward function that's always 1. Perhaps taking the summatory function of other simple functions could create interesting things. For example, if you start with the pretty straightforward function f of n equals n and take its summatory function, you get what's called the sum of divisors function, which we denote as sigma of n. So what you find is that sigma of n is the summatory function of this function f, but f of n is just n, so f of d is just d. So sigma of n simply goes, what are the factors of n? Add all of them up. Hence it's called the sum of divisors function. So little f of n is a multiplicative function, and therefore so is sigma. To compute the values that sigma takes, we therefore only need to know how it works on prime powers, and that's actually pretty straightforward. Okay? Sigma of p to the k, we simply sum up all the divisors of p to the k, so we sum up 1 plus p squared up to p to the k. This is a partial sum of a geometric series, or a geometric sum, which has a nice formula. Taking the sum of powers of p ending at p to the k is the next power minus 1 over the base minus 1. So here is the sum of all of the positive factors of p to the k. It's p to the k plus 1 minus 1 over p minus 1. So as an example, let's try to sum up all the positive factors of 100. Now what we could do is we could list them all out and sum them, but what we could do instead is say the sum of divisors function is multiplicative, and the prime factorization of 100 is just 2 squared times 5 squared, then I rely on this formula here. Sigma of 2 squared, the prime and the power are both 2, so I get 2 cubed minus 1 over 1. There we have it. Sigma of 5 squared, now the prime is 5, but the power is 2, so I get 5 cubed minus 1 over 5 minus 1, or 124 over 4. 7 times 124 over 4 is just 217. 124 over 4 is 31. So what's the sum of all the positive factors of 100? It's 217. You know what we didn't do? We didn't list out all of the positive divisors of 100 and then manually add them up. That would have actually taken much longer. So we've learned a handy little parlor trick. So if you're at a party and conversation reaches an unnatural lull, you can simply announce, hey, who wants to watch me compute the sum of all the positive factors of 12,000? Then you pull out a piece of paper and you do it, and everyone walks away.